Welcome to today's video. I'm trying a new format. Comment down below how you like it. I'm Ivan. Let's get into it. Forget sci-fi tropes. A black hole isn't a cosmic vacuum cleaner roaming around sucking up galaxy clusters. It's a boundary condition of space-time, a region where gravity has completely overcome all known fundamental forces. To understand how a black hole works, let's start with the simple explanation. Every object with mass has an escape velocity, the speed you need to launch a rocket so it breaks free from gravitational pull without further thrust. Earth's escape velocity is about 11.2 kilometers per second. If you compress Earth's mass into a smaller volume, its surface gravity goes up and its escape velocity rises. If you compress Earth down to the size of a marble, its escape velocity crosses 300,000 kilometers per second, the speed of light, c. Because nothing in the universe can travel faster than c, nothing, not even light, can escape. It's an optical trap. Now, here is the advanced, accurate explanation. Black holes aren't about sucking light in, they are about the geometry of space-time. In general relativity, the path of light defines what we call light cones, the set of all possible future paths a photon can take from a given point. In flat space-time, your light cone points straight up into the future. As mass curves space-time, those light cones tilt toward the mass. At the event horizon, the light cone tilts so severely that its outer edge becomes parallel to the horizon itself. Once you step inside the event horizon, the light cone tilts past 90 degrees. All future-directed paths, every single null and time-like geodesic point strictly inward toward the center. Inside the horizon, space and time effectively swap mathematical roles. Moving toward r equals 0 is no longer a spatial direction you can choose to avoid. It is an inevitable moment in your future timeline, as relentless as next Tuesday. In 1916, amidst the artillery fire of World War I, German physicist Karl Schwarzschild derived the first exact solution to Einstein's field equations. G mu nu equals 8 pi g over c to the fourth power times t mu nu. Schwarzschild assumed the simplest possible case, a static, non-rotating, spherically symmetric mass in a vacuum with zero electric charge. The metric describing the space-time geometry around this object is the Schwarzschild metric. ds squared equals minus, open parenthesis, 1 minus r sub s over r, close parenthesis, times c squared dt squared plus, open parenthesis, 1 minus r sub s over r, close parenthesis to the power of -1, d r squared plus r squared, times, open parenthesis, d theta squared plus sine squared theta d phi squared, close parenthesis. Look at those terms in parentheses. Notice 1 minus r sub s over r. When the radial coordinate r equals r sub s, that term becomes 0. The dt squared term goes to 0, meaning coordinate time halts for an outside observer, and the dr squared term experiences a division by 0, an apparent mathematical singularity. That critical radius r sub s is the Schwarzschild radius. We can derive it classically by setting escape velocity equal to c 1/2 mv squared equals gmm over r, which implies c squared equals 2gm over r sub s, which implies r sub s equals 2gm over c squared. Let's plug in numbers for Earth, where mass m is approximately 5.97 times 10 to the 24th power kilograms. R sub s is approximately 8.87 millimeters, about the size of a peanut. For our sun, where mass m is roughly 1.989 times 10 to the 30th power kilograms, R sub s is roughly 2.95 kilometers. Around a Schwarzschild black hole, two other key boundaries exist. First, the photon sphere at r equals 1.5 r sub s, or 3g m over c squared. Here, gravity is so intense that photons are forced into unstable circular orbits. Stand here with a flashlight, and light rays emitted from the back of your head orbit around and enter your eyes, you would literally see the back of your own head. Second, the innermost stable circular orbit, or ISCO, at r equals 3r sub s, or 6gm/c squared. This is the absolute limit where matter in an accretion disk can orbit stably. Cross inside 3r sub s, and matter can no longer orbit. It immediately plunges inward. Crucially, r equals r sub s is merely a coordinate singularity, a artifact of our chosen coordinate system, like the lines of longitude converging at Earth's North Pole. If you switch to Eddington-Finkelstein or Kruskal-Sekhar's coordinates, the math at r sub s remains completely smooth. The true physical singularity is at r equals 0, where the Kretschmann scalar k equals r alpha beta gamma delta times r alpha beta gamma delta, which is proportional to m squared over r to the 6th power, approaches infinity, density becomes infinite, and classical general relativity breaks down entirely. Schwarzschild black holes are elegant, but in the real universe, almost nothing sits completely still. Stars rotate. When a massive star collapses, conservation of angular momentum forces the core to spin at violent speeds. For nearly 50 years, physicists couldn't solve the math for a spinning black hole until New Zealand mathematician Roy Kerr solved it in 1963. Enter the Kerr metric. Kerr black holes are parameterized by two values: total mass m and spin parameter a equals j over mc, where j is angular momentum. Because of rotation, a Kerr black hole is not spherical. It's an oblate spheroid with a complex inner structure. First, rotation drags space-time itself around the black hole, a phenomenon known as frame dragging or the Lense-Thirring effect. This creates an extra region outside the event horizon called the ergosphere. The outer boundary of the ergosphere is given by r sub e of theta equals gm/c squared plus the square root of open parenthesis gm/c squared close parenthesis squared minus a squared cosine squared theta. Inside the ergosphere, space-time is dragged at a speed exceeding c relative to the distant universe. You can still escape the ergosphere if you fire rockets against the rotation, but you cannot physically stand still relative to an observer at infinity. Space-time itself is sweeping you along. A Kerr black hole possesses two event horizons, an outer event horizon R+, and an inner Cauchy horizon R-. R plus or minus equals gm/c squared plus or minus the square root of open parenthesis gm/c squared close parenthesis squared minus a squared. If the spin parameter a reaches gm/c squared, R plus and R minus collapse together. This is a maximal Kerr black hole. If spin a is greater than gm/c squared, the horizon disappears entirely, exposing a naked singularity, a catastrophic scenario that the cosmic censorship hypothesis posits is physically impossible. At the center of a Kerr black hole, centrifugal force alters the singularity itself. It is no longer a zero-dimensional point, but a ring singularity in the equatorial plane with radius a. Even wilder, because of the ergosphere, you can extract energy from a Kerr black hole via the Penrose process. If a particle enters the ergosphere and splits into two pieces, one piece can fall into the horizon on a negative energy trajectory, while the other piece escapes with more energy than the original parent particle had. You are literally stealing rotational energy from the singularity. Up to 29% of its total mass energy can be harvested this way. So how do you actually manufacture one of these monstrosities? Physics gives us three primary mechanisms. Recipe 1, stellar collapse or astrophysical black holes. When a star with a starting mass above roughly 20 solar masses exhausts its nuclear fuel, thermal pressure drops, gravity wins. The core collapses. If the remaining core mass exceeds the Tolman-Oppenheimer-Volkoff, or TOV, limit roughly 2.2 to 3 solar masses neutron degeneracy pressure fails, nothing in known physics can stop the collapse. The core plunges inside its own Schwarzschild radius, triggering a type 1b, 1c, or 2 supernova, leaving behind a stellar mass black hole. Recipe 2, primordial densities, or cosmological black holes. In the first 10 to the negative 23rd power seconds after the Big Bang, the universe was hyperdense. Random quantum fluctuations created regions with local density perturbations, delta, rho over rho, greater than or equal to 0.3. These regions collapsed directly into primordial black holes without needing stars at all. Their masses could range from 10 to the negative 5th grams up to thousands of solar masses. Recipe 3. High energy compression or micro black holes. To turn any subatomic particle into a black hole, you must pack its energy into a volume defined by its Compton wavelength equal to its Schwarzschild radius, the Planck scale, approximately 1.22 times 10 to the 19th power giga electron volts. At current Large Hadron Collider energy scales, roughly 13 to 14 tera electron volts, we can't do this. However, if extraspatial dimensions exist, as predicted by string theory models, the effective Planck scale drops down to the tera electron volt range. Particle collisions could theoretically forge microscopic black holes that evaporate instantaneously via Hawking radiation. T sub h equals h bar c cubed over 8 pi gm k sub b. From Karl Schwarzschild's static mathematical curiosity to Roy Kerr's spinning cosmic dynamos, black holes represent the ultimate extreme of general relativity. They are places where space becomes time, where spinning space-time can power relativistic jets across galaxies, and where quantum mechanics and gravity are forced to meet at an infinitely dense point. They aren't just holes in space, they are the end of space and time as we know it. Thanks for watching.
Have an amazing day or night wherever you are. See you in the next deep dive. Comment down below how you like this format. And as always, like and subscribe.